Who here is ready to learn about Shasta River water temperatures? Raise your hand. All right, great. Okay, so pretty much everything that I'm presenting today is comes from Appendix A and Section 4 of the Shasta River Canyon in-stream flow assessment. And that was there's no way to get rid of this thing, is there? It's just there. You keep talking. Okay. Oh, sorry. Yes, so I was the primary author of the water temperature analysis for the Shasta in-stream flow assessment. Suzanne Rhodes and Scott McBain with Applied River Sciences were also co-authors on that. And then Applied River Sciences led the broader in-stream flow assessment. But we're here to talk about the temperature part of the in-stream flow assessment. To understand water temperatures in the Shasta River and how to understand and model the effects of flow on temperatures, we need to understand something about how the system has changed over time. Because I think relative to most places, there's been probably bigger changes in the Shasta in the last 20 or so years than other places. I'm going to touch on the need to do more effort to round up the data that has been collected. I'll do a brief summary of some of the previous modeling work that's been done. I'll spend a good amount of time talking about the temperature modeling that I did, and then I'll talk about some implications for developing in-stream flow regulations. So we'll start with the history stuff. And so I went through the recent history of the Shasta, like the last 20 years or so, and divided things into things that I think would decrease water temperatures, things that didn't change it much or mixed effects, and things that would increase water temperatures. And there's more detail in the report, but I'll just touch real quick on a subset of the more important ones. So I think the biggest one was the curtailments by the State Water Board, where access to irrigation water was restricted. That generally resulted in higher river flows in the late spring and early and summer. Also, the Big Springs Irrigation District's groundwater use was curtailed for the first time ever. And now actually they have become the most junior of all the large water users in the Shasta. They're the first to get shut off. And so that theoretically has increased flows in Big Springs Creek, although we didn't really have the data to show that. There was riparian fencing in Big Springs Creek that went in when Nature Conservancy acquired that property, now managed by California Fish and Wildlife. There's been a series of removals of small dams along the main stem of the Shasta. The Cardozo Ranch used to, they impounded Parks Creek in this big pond and then took the water from there. And they changed the irrigation source to remove that impoundment, let the cold water from the springs flow down Parks, and now they divert their water at the main stem of Shasta, several miles downstream. And the surface diversions from Big Spring Creek have been reduced. There's less irrigated area there now as a result of the Nature Conservancy and California Fish and Wildlife. Although I don't really know how, I'm not sure what the current system is for tracking those surface diversions. Some things that I think have had very little effect on temperatures in the main stem is all of the riparian fencing and riparian restoration. There's been a big effort to fence cattle out of the streams and to plant trees, but it's really not providing enough shade to meaningfully change temperatures in the river, and not even really enough to keep up with the decaying of all the old trees that are there. They're not being replaced. Things that have probably increased water temperatures is global climate change. So, hotter air temperatures means hotter water temperatures, but then there's also the hydrologic effects. So, less snow, more rain. And then also I think one that's underappreciated is rising air temperatures increases the atmosphere's water demand. So, growing an acre of irrigated pasture or just an acre of natural vegetation like a forest, those are all using about 10% more water than they were about 40 years ago. And so that has, I think, big effects. So there is also evidence of increased groundwater extraction and reduced groundwater recharge at Big Springs. The biggest of these was the lining of the Montague Water Basin Water Conservation District canal. Studies from before that lining showed that about half the water that was lost, quote unquote, lost in the transmission along that canal was right in the vicinity of Big Springs Creek. And so they got a lot of public money to line that canal and cut down on that recharge. So they're delivering more water to their endpoint. But of course, that water that was seeping into the ground before, it wasn't really lost. It wasn't water was destroyed. It was water that was going into the ground and then coming up at the springs. So we've got less recharge now. A lot of the farms that pump groundwater into the geologic unit that provides water to Big Springs got solar panels installed, primarily around 2016, 2017. So that may have, we don't really have data for it, but it could have reduced their cost to extract water and reduced the incentives to use less water because it's more expensive now, or it's less expensive now. And then there is the cannabis farms in the Mount Shasta Vista subdivision at the southeast corner of Shasta Valley. You know, there are established methods for estimating water use at cannabis farms, and that's been developed by UC Berkeley and others and deployed around the North Coast. But as far as I know, nobody has quantified this yet. It's a potentially significant amount of water. And so I would encourage the county or state water board to quantify that. Somebody needs to do it. So all those things I think have increased, pushing in the direction of increasing water temperatures. I compiled a ton of flow data and temperature data. Here is just a gobbledygook plot showing flow data, period of record at different sites. That's more for future reference. But there were some really important data sets I was not able to get a hold of. So for example, the UC Davis and Nature Conservancy flow gauge on Big Springs Creek, there was a really great record, continuous record of flows from 2008 to 2015, and I can't find the electronic data for that. So really the only place that data exists, as far as I can tell, is either in reports like this. So we might have to go through, someone has to go through and kind of digitize these values from the plot, or it might be in a backup hard drive in a closet somewhere. But there is really important data that does need to be rescued at some point. There's been a lot of previous, obviously I'm not the first person to look at water temperatures in the Shasta River. It's been happening for decades. Great work by UC Davis, Water Course Engineering, as part of the North Coast Water Board's TMDLs and projects for the Nature Conservancy. So there was all this, there were these models that were developed for Shasta River and Big Springs Creek. They ran put a lot of work into this, ran a lot of scenarios and wrote a ton of reports and publications where they did a lot of different scenarios that show things like the importance of what it does to, say, increase spring flows by a certain amount compared to decreasing diversions by a certain amount. And really interesting insights there that I try to summarize in the report. The biggest gap that I identified was that none of the physics-based models for Big Springs Creek have been run on simulating what would be an unimpaired flow for Big Springs Creek. There was some kind of back of the envelope calculations for the TMDL, but we really don't know, what temperatures in Big Springs would be like under unimpaired flows. None of these models is also, available off the shelf to just start using and run different scenarios. So they're not available at the present moment. The State Water Board and its contractors are developing a new model, but it's still in development. And so for the Shasta Canyon in-stream flow study, I developed some statistical models to help out with that project. And of course, water temperatures are a big issue in the Shasta. The water's too hot in the spring and summer, too hot to be ideal habitat for fish. So we wanted to look at how does flow influence temperature, and the outputs from the models that I did become the inputs to the fish bioenergetic models that Suzanne and Kevin will be talking about in the next presentation. So I'm kind of trying to set the stage for them here. And we also wanted to understand not just the flow temperature relations in the Shasta River Canyon at the mouth of the Shasta, but also how would higher flows in the canyon translate into higher flows and cooler water upstream all the way up into Big Spring. So our focus was a canyon, but we did do some wider things. So I developed a generalized additive model to predict daily water temperature as a function of flow, air temperature, day of the year, curtailment status, and what I'm calling era, it's a time period. Because it did seem in my preliminary analyses that for a given flow and air temperature, water temperatures are cooler in the last 16 years or so than they were previous to that. So I put that kind of a binary effect in there for which time period we're in, which era. One caveat on these empirical statistical models is that you really can't push them too far out of the bounds of the calibration data that were used to construct the models. So for that reason, we didn't run flow scenarios in July and August at more than 100 CFS, even though unimpaired flows are maybe 50 or 100% higher. Also in these models, we're just lumping all the source waters together. We're saying, okay, the flow at the mouth of the Shasta River is 20 CFS or it's 100 CFS. We're not trying to track, was that a reservoir release and how much of that came from the springs and how much came from Parks Creek. We're just lumping it all together. So we're probably underestimating the effects of flow, at least as far as if the flow would be just like pure spring water. So it's kind of a mixed source water. So I developed these models at 6 different sites, from the water wheel on Big Springs Creek down to the mouth of the Shasta River. We calibrated it using the whole 30-year data set, but then we only ran the scenarios on the most recent era. All the models use the flow from the mouth of the Shasta River. So, for example, to model temperatures at Shasta River at A12, we'd pair flow from the mouth of the Shasta with temperature data that was collected at A12. And we did that just because there's not enough flow data at the other sites. And then we did do some integration to the whole Shasta River by just linearly interpolating between our 6 sites that we modeled. These effects plots show how daily mean temperatures vary by the different flow scenarios or different lines. And just to summarize it here in the interest of time, one thing that's interesting is that even accounting for flow, so the difference between like 10 CFS and 100 CFS is about 1 degree Celsius. But the curtailment status itself, whether the curtailments were in effect or not in effect, also cooled it down about another 3/4 of a degree. So the combined effects of, say, comparing 10 CFS without the curtailments in effect versus 100 CFS with curtailments in effect, that difference is about 1.8 degrees Celsius. Here's the same plot, but for daily maximum temperature, and the effect about doubles. So 100 CFS with curtailments in effect is about 3.6 degrees colder than 10 CFS with no curtailment in effect. We looked at exceedances of a lot of different temperature thresholds. That's what the colors are, is the percent of days exceeding temperature thresholds. On the x-axis there is different flow scenarios, and it's every 15 days through the summer are the columns there. And we see that below about 50 CFS, a lot of these temperature metrics, you add a little bit of flow and you get like a big amount of cooling. And then as you continue to increase flow, water continues to get colder, but it starts to kind of level off. You still do get colder water the more flow you add. And our model, we had to stop it at 100 CFS, but I would expect that those cooling would continue with even higher flows all the way up to unimpaired. We also looked at how high flows protect against like critical lethal temperatures. So on the x-axis here is flow, the y-axis is daily maximum temperatures, and these are measured temperatures, not the modeled. And so you see the scatter plot here, there's a general trend, right, of you've got higher flow, you have cooler temperatures. There's also a lot of scatter in there because there's other things like air temperature and day that affect these. But one of the really interesting results is that the record high water temperatures don't coincide with when record high air temperatures occur. When we set the record for hottest water temperatures was when flows were pretty low, say under 25, 30 CFS. When we had record high air temperatures in late July of 2022, the curtailments were in effect. The flow at the mouth was 50 CFS, and temperatures still got pretty hot, but they didn't get nearly as hot as they did during periods when air temperatures were cooler, but flow was lower. So there's that protective effect of high flows mitigating the worst temperatures that we see. Here's just a quick example of the whole river results. And I'll just say here that if we here to say increased flow from 50 to 100 CFS, you get about 50% more habitat that doesn't exceed 22 degrees Celsius. So the higher flows at the canyon, at the mouth of the Shasta, the water's cool by the time it comes to the mouth of the Shasta. That means there's also cooler water all the way upstream. So wow, I'm talking really fast, I guess. Some key implications for in-stream flow recommendations is that below had its biggest effects on daily maximum temperature. It was about twice as great as the effects on daily mean. Higher flows allow cool water to last further into the summer season. High flows reduce those acute high thermal stress that can occur during heat waves. And higher flows in the canyon are associated with cooler temperatures upstream as well. And that even once we account for a flow, say the flow at the mouth is 50 CFS, if it's 50 CFS because the curtailments are on, the curtailment has additional cooling beyond just what the flow is. There's something about the process of what happens when the water board orders curtailments that cools the river down, other than just increasing the flow. So I think the two biggest things is probably the curtailment of Big Springs Irrigation District, and then also if there's people who are flood irrigating who don't get their water when the curtailments are on, then there's less tailwater coming back into the river. I think that's probably the two things. So I didn't really include it in my modeling here, but based on the previous research, this location of where water comes from and where it goes has really big effects on temperature. So for example, the spring water is cold. Some of the tributaries are cold, some are warmer. The reservoir releases in the summer are pretty warm. So it really matters where that water is coming from. Not all water is created equal. In addition, the location of water extraction matters a lot for temperature. So if you're diverting water right at a spring source, or you're pumping groundwater that would have ended up in that spring, that's going to have the most substantial effect on temperatures from a fish habitat perspective. If you're diverting water that's already been in the river for 30 miles and you're diverting it from the main stem river and it's already heated up by that time, that's going to have a less effect. And so there's a general concept here that if we move diversions downstream, we can improve temperatures, even if we're not really changing the amount of agricultural land, or we're not changing the amount of water that makes it out of the Shasta down to the Klamath. Just by moving diversions downstream, we can improve temperatures to a certain extent. Obviously, if you didn't divert at all, you have more benefits, but there's some benefits can happen just from moving things downstream. And yeah, I got through that like way faster than I thought I was. So, big questions. But actually, no, it wasn't faster. I forgot about it. It was 15 minutes, not 20. Okay.
All right. Questions, Laurel?
Eli, with the maximum temperatures being affected even more than the mean temperatures, did you see, is there a difference in the time of day that maximum temperature is hitting? Is there a shift? Kind of in
good question. The Shasta is like a weird beast with thermal signals from springs propagating downstream, so there might be. I think the main thing is that the also made one of these plots for daily minimum temperature, and the lines are essentially right on top of each other. Like changing the flow doesn't really change the minimum temperature. It changes the maximum temperature a lot, and so then the average temperature is kind of in the middle of those two. Yeah. Any other questions? Yeah, Ben.
Do you think it doesn't affect the minimum much if you're not able to control where the water's coming from? Like if you fit it, signal all your water unimpaired big spring flow, if the minimum line still all be on top of each other, or would you start to have a lower flow?
Yeah, he's asking. Ben's asking if the why we don't see an effect on effective flow on minimum temperatures is because we're just considering all the water lumped and not isolating spring flow from springs. I think that is potentially true. Yeah, there's also things like, I think it's less than 1 day's travel time. It might be like 12 hours travel time, like say from the head of Big Springs down to the mouth of Big Springs. And so at night, the water just doesn't warm up that much. And then if you have high flows, it's like there's less warming that happens during the day. But I think nighttime temperatures in the Shasta definitely cools down more than some other places do. Yeah, Michael.
If you go back to your map of Shasta.
Yeah.
So it's 5% of the Shasta River is just going into the dam and being warmed up, right? The upper Shasta.
Yeah, the dam is catching the upper runoff, and from Parks Creek also, they divert Parks Creek over into there. And then actually, yeah, so it's basically captured. Very little of it is released into the river. Most of it goes for, there's actually a huge amount of seepage into groundwater recharge, and then the rest of it goes through that canal to the North Valley for irrigation.
So what happened? I mean, I'm sure people have thought about this, but if you made a connection from the upper Shasta to Parks Creek above the dam, and that cold water could continue around the dam and stay in the river. Have you ever thought of that?
During summertime, the water's not cold coming into,
even though it's
the river.
coming.
It probably is. I think it is cold during the snow, like during peak snowmelt. But yeah, not during the middle of the summer.
It just seemed like it's getting warmed up in the dam, but okay,
Yeah.
Thank you.
You would get a lot higher flows in the springtime, and you get salmon swimming up there above doing all. You get higher flows in the springtime. Probably like early summer, you might get warmer temperatures because you'd have, like the water coming down the Shasta River is warmer than the water coming from Big Springs. So at certain times of year, having more water coming from upriver would make it warmer. So there's costs and benefits, to everything.
Okay. And
Yeah.
Eli, with all the water temperature data you've dealt with, how many millions of records of water temperature data do you have? Ballpark.
80 million? Maybe?
80 million
I don't know.
water
Like
temperature data points.
Yeah. In the Klamath Basin.
You're an animal.
Yeah.
Yeah. Any other questions? All right, Eli. Well, thanks so much for your analysis and presenting on this.